Swayam Prabha. Digital India. Educated India.
In this lecture, we continue our discussion on compressible flow, where we look in a more detailed manner on shock waves and in specific normal shocks. So, in the previous lecture, we were discussing about characteristics and then we were discussing about finite waves. And if you recall, we said that finite compression waves can lead to shocks, and we were trying to represent the motion of a finite wave in the xt plane, which is a very convenient exercise when it is a one dimensional flow, because the displacement of the wave takes place only along the x direction, and we can follow the wave both in space and time when we make a xt plot. Just for recollection, we said that a very small amplitude pressure wave which we called as sound wave, when it propagates through the medium, the ripple that is created in the flow properties traverses through the domain at constant speed, that is at the sonic speed, and the wave form remains undistorted as it traverses through the medium. We said that these lines are the characteristic lines. And we see these characteristic lines in wave propagation problems. In a mathematical sense, they belong to the family of hyperbolic partial differential equations. We said that characteristics can be moving either along the positive x direction or the negative x direction, and therefore, there are two families of characteristics which are possible. So, the ones which are moving towards the positive x direction may be called as right running characteristics, and those running to the left could be called as left running characteristics. Based on the characteristics approach, we have the so called method of characteristics, abbreviated as MOC, as one of the very powerful methods for computing inviscid compressible flows. So, if the flow is irrotational, then it is slightly easier to implement the MOC technique, but even if it is rotational, you do have a rotational form of the MOC technique as well. When the wave becomes a stronger wave, then the characteristics can interact. In the case of weaker waves, the characteristics are going to travel through the medium independent of each other, and then all of them are going to travel at the same speed. While for stronger pressure waves, characteristics can interact. And since in this lecture we are going to look at shock waves, let us revisit the nature of the characteristics when we look at shock wave formation. So, we are marking the shock formation with the red line, and we are seeing that characteristics are interacting with each other, forming the shock wave. When do they interact forming a shock wave? When characteristics of the same family merge together. Why are they merging? Because different characteristics are moving with different speeds. These are the comparatively faster moving characteristics, and these are the slower ones. When we talk about strong pressure waves, the presence of high pressure gradients within the flow also induce a flow velocity in the bulk sense, and in such a situation the dx dt of the characteristic waves are not only influenced by the value of A, that is the sonic speed, but also by the local flow velocity. And the local flow velocity is certainly a function of x and t. For strong pressure waves, even A can be a function of x and t. Now, if you were to look at the nature of the velocity, then you may have a variation like this. And you will find that the variation becomes sharper as you move in time, and once the shock forms, then there is a real sharp change. So, that is how from a comparatively smoother variation you have a sharp change in the form of a shock formation. So, the wave front changes its shape as the wave propagates. In space and time for a strong pressure wave. These are often called as nonlinear waves. When can shock occur in nature or in engineering applications? Let us think about a few examples where in particular we have a special kind of a shock which is called as a normal shock. Normal shock is by and large a one dimensional shock structure. Like you are seeing here in this case, there is a sharp change. What changes about it? It is essentially the variation of the flow property. So, if it was a velocity distribution u, then there is a sharp change in u about the shock. That means, only one component of velocity has changed here, it is the u component. Thereby, we are talking about a one dimensional flow associated with normal shock. So, the flow across a normal shock is basically one dimensional. Where can normal shocks occur? If we try to answer that question, let us imagine a cylinder with a piston and air ahead of the piston, and then you are moving the piston very rapidly towards the right. If the compression is really very huge ahead of the piston, that can lead to shock formation. If you have a supersonic flow approaching a flat surface, there could be a shock formation ahead of the flat surface. If you have a flow through a converging diverging duct or a nozzle, and you are expanding a high pressure gas through this duct, if the flow accelerates from a subsonic condition to a sonic condition at the smallest cross sectional area, which we call as the throat, and then it turns supersonic beyond the throat. If it is not able to adjust with the pressure which is lying outside the nozzle, which we call as the back pressure, and the back pressure happens to be higher than the pressure that is existing in the flow here in the supersonic portion, then a shock may be formed here in the diverging portion of the nozzle, so that the flow is able to adjust with this back pressure before mixing with the ambient. So, these are instances of normal shocks. Why at all is a normal shock formed? From a molecular motion perspective, we have tried explaining it earlier from the characteristics point of view. Now, let us try to explain it from the microscopic point of view, that is through the molecular motions. So, molecules are moving around in the gas, and when the flow is approaching the solid wall here, the flow is reaching the wall and the molecules are colliding with the wall, and then they are colliding with their neighbors and trying to percolate this information all around that there is a wall. This is happening because increasing number of molecules are impacting with the wall, colliding with the wall, and thereby feeling the presence of the wall, they collide back with their neighbors, trying to propagate this information upstream that there is an obstruction. At what speed does that information propagate upstream? It propagates at the speed of sound, the sonic speed. At what velocity is the flow approaching the wall? It is propagating at more than sonic velocity, because you have m greater than 1, and by definition m is v by a. So, what happens effectively is that though these molecular collisions are propagating upstream, trying to spread the information through these disturbances, they do not manage to go far upstream, because the incoming flow is higher than the sonic speed. The sonic speed is not sufficient for the disturbances to propagate far upstream, and therefore, at some point there is accumulation of disturbances forming the shock. And because of the geometric nature of the wall, the shock has a flat structure, which we are calling as a normal shock. In this situation too, the moving surface which is creating the compression is flat in nature, and therefore, the high pressure front which finally forms a shock wave ahead of it also has a flat nature, which is again a normal shock. So, in nature we also observe shocks which are tilted to the flow direction. Those are called as oblique shocks. We will deal with them in due course. Let us try to look at a one dimensional control volume, and let us imagine that a normal shock lies within this one dimensional control volume. We will say that the flow is approaching from the left to the right. This is the flow direction. This is the normal shock, which is actually a very, very thin region. Typically in air at standard conditions, it is as thin as of the order of 10 to the power of minus 5 centimeters. So, when the flow approaches the normal shock, it has some accompanying properties. Let us say the velocity is u1, pressure is p1, density is rho 1, temperature is T1, internal energy in specific sense is E1, and so on. You can further say enthalpy and other properties including entropy. And then after the flow crosses the normal shock, let us define the properties like this. And let us try to figure out that by applying the conservation laws, how can we connect these sets of properties across the control volume. So, for that we will recall our conservation laws and we will apply them in an integral form. So, we remember that there are finite changes which are occurring across the control volume in place of infinitesimal or differential changes which occurred in the case of a sound wave. You would recall that in the case of sound waves, we had shown the differences in differential amount form, while here the changes are finite. Let us try to write down the continuity equation in integral form, and of course, we will make certain approximations. Let us say we are looking at steady flow, in which case the time derivative term will go away from the equation and there will be only one term left, which when applied to this control volume will be in this form: A times rho 1 u 1 equal to A times rho 2 u 2. It is because the cross sectional area does not have any variation across those stations 1 and 2. Let us call these as stations 1 and 2. So, what we are trying to say is A 1 is equal to A 2 is equal to A. Therefore, the area term cancels out and we are left with the continuity equation in this form. So, this is the mass conservation across a normal shock. What about the momentum equation? Since we are talking about a one dimensional flow, therefore, it is sufficient if we look at say the x component of the momentum equation, and when we do that, the integral form of the equation will contain two terms on the two sides of the equation. This is the advection term, and we are going to have the pressure term on the other side of the equation. So, what all other terms are we neglecting? The time dependent term is neglected because we are assuming a steady flow. Then we are assuming it to be an inviscid flow. So, viscous terms on the right hand side of the equation will not be there, plus there are no body forces. So, these are the approximations that we are doing. That means, we are essentially talking about inviscid compressible flow across a normal shock. Additionally, this inviscid flow is a steady flow, plus there are